Hello everybody, so in this video we will be looking at the LeetCode problem 62, that is unique paths. So the problem statement says that there is a robot on a m cross n grid, so that we are given a m cross n matrix, and our robot is initially at the grid 0 0, that is the top left corner, and the robot tries to move from the top left corner to the bottom right corner, that is m minus 1 and n minus 1. So we are also given that the robot can either move down or right. So either I can move to the right or to down. So we are given the size, that is m cross n, and we have to return the possible path that the robot can take to reach the bottom right. If we take for example, if we take a 3 cross 3 or 3 cross 4 matrix, so if I draw this, so this is my 3 cross 3 grid or matrix. I'll give the indexes. So here my robot is positioned at here. So what we can do, and we have to reach here, destination D. So either we can move right or we can move down. So what this robot can do, it can move right, then it can again move right, then it can move down, and then it can move down. We got one way to reach the destination. Another way is it can move right, it can move down, it can move down, it can move right. We got another way. Okay, so another way is we can move down, we can move down, we can move right, we can move right. Another way. Now another way is if I say another way is from here I can move down, then I can move right, then I can move down, then I can move right. I got one more way. Then there is another way. From here I can move right, I can move down, I can move right, I can move down. I got another way. So in total I got 5 ways. So this is what we will have to return in the end, that is 5, the answer. So if I again draw a matrix, I'll just take a small matrix of size okay, so I'll take a small matrix of size 3 cross 2, and I am initially at this position. This is my start, right, and this is my destination. So at a certain grid or a certain cell, suppose this is a cell 0 0, what I can do, I can either go right or down, or I can either go right. So I can either go down, that's fine. So I can either go down. So if I go down 0 1 2 0 1, if I go down I'll reach here, my robot is here. Okay, and if I go right, if I go right, my robot is here. Now from here I can again go down, or I can again go right. So if I go down, so this one is for down, down. So if I again go down, so I'll reach here. This is the path I have taken, and I'll reach here. This is my start, 0 1 2 0 1, and this is my destination. And from here if I go right, from here if I go right, so this is the path I have taken, and at the moment I am here. So it's in the recursion, as you can see, we are trying all the ways, so it is a recursion. So in recursion, what we will do, first the left side is solved. So from here, first of all we will solve this one. So from here I can go down again. So if I go down again, as you can see, I am here, I am here. If I go down again, I will go out of my grid. So what I'll do, I'll return from here, that I cannot go there, so I'll just return a 0. I'll return a 0, that there is no way, so I'll return a 0. Now from here I can also go right. So I am here, So now I reach right and I am at my destination 201. So I am at my destination. So I have reached, that is m minus 1 n minus 1. So this is my base case, that when my I equals to m minus 1 and my j equals to m minus 1, that is I have found a way in the grid to go from start to the end. So I'll return a 1, that I have a way. Similarly, I can expand these subtrees, like from here I can go down, or I can go right. So if I go down, I'll reach here, but if I go right, I'll reach out, so I'll return a 0. And similarly I can do for this. So now let me just discuss the pseudocode for this. So we have a function and we will be passing a I and j initially. If you wanna go something like this, so for example, if I am here, I can reach here from this point or this point, right? So I can either move backwards, like by going instead of going down, by up, and instead of going to right, I can go to left. So either I can take initially, if I start from here, so I can initially take I as 0 and j as 0, and I'll go till m minus 1 n minus 1. And if I initially take them as m minus 1 n minus 1, then I'll go till I equals to 0 and j equals to 0. So I am taking I initially as 0 and j initially as 0. So my base case was, if my I equals to m minus 1 and my j equals to n minus 1, that is I have reached this destination, so I'll return 1. Now we had another base case. What was that base case? That base case was, if I go out of my grid. So in that case, if I see, if my I is greater than or greater than equal to m, right, and or my j is greater than equal to n. So I have gotten out of my grid, so I'll return a 0. In the end, what I am doing is I am finding all the ways. So if I am getting a way, I will just add all those ways. So in the end, I'll just return by going down. So if I am going down, suppose I am here, and if I am going down, what is changing? My I is changing, my row is changing, and if I go right, my j is changing, my columns are changing. So for the right call, I will pass I plus 1 j, plus for the left for the right call, I will pass I comma j plus 1. So that is the recursive code for this. Now to convert this recursive code into a memoized code is very easy. What we will take a dp array of size m cross n. We will take a dp array of size m cross n, and I'll initialize it with -1 initially, and we will add a single statement here. If I have already computed this, no need to call the recursion call, and just return this answer available. And here we will add dp of ij equals to this. Okay, similarly what we can do is, just like this, as we have started from 0 and we are going to m minus 1 n minus 1, we can do another thing. We can start from m minus 1 to n minus 1, and we can go till 0 for both of these values. And what we will do, then our base case will change something like this. If my I equals to 0 and my j equals to 0, I'll return 1. And this one will be, if my I is less than 0 or my j is less than 0, I'll return a 0. This will be a minute change if I take it as something like this. If I have done this and I'm calculating for the rest. So, and in where I was going right, I'll go left. Where I was going down, I'll go up. That is what I will do. So if I now code this, if I just code this, we have just two approaches. I'll code the second one. I'll code this one, or I can code this one too. Let's see. But if I code this one, I have to pass two more variables along with m and n. So I'll just code the second one. So what I'll take a vector, 2D vector, int dp of size m I'll initialize it -1. Now I'll return my function. I'll pass m-1, n-1, and I'll also pass the dp array. Now let me just define this function. In function, I'm expecting I'm expecting an integer another, and I'm also expecting a 2D vector. I'll take it as a reference. Now my base condition was if my I is equal to 0 and my j equals to 0, I'll return a 1. If my I is less than 0 or my j is less than 0, I'll return a 0. If I've already computed for that index, this is where memoization comes into play. I'll just return dp of ij, as we will not again calculate this, so it saves in time complexity and decreases time complexity. In the end, I'll just return my function calling on i-1. I-1 means if I'm here for right, I was going if I am here for down, I was going here, I was increasing. For instead of down, I'll go up and I'll do a -1, and similarly we will do for my right one, that will be I comma j -1 comma dp. Now if I submit this code, okay, so we get a TLE because I have to write here dp of ij. It's not, if I do it like this, it's not memoized, so that was the mistake. So if I submit it again, it should be submitted now. So as you can see, our solution is accepted. So if I discuss the time complexity and the space complexity of this problem, so the time complexity here is is order of n, as we are just the maximum depth of the recursive tree, that is the time complexity, and the space complexity will be order of n for the auxiliary stack space we are using in our recursion calls, and as well as order of n square for my dp array, dp matrix, that is. So we can further optimize this using the tabulation form. I'll discuss this approach in the next video, so make sure that you watch the next video. So in that video, the time complexity will remain order of n, but the space complexity will turn out to be order of n square only. We will omit this auxiliary stack space, and we can also even further space optimize this, that will have a time complexity of order of n and a space complexity of order of n. That is a space optimized, but we can keep it till here also, that is not an issue. So I'll discuss this approach in the next video. So thank you for watching this video, and please subscribe to the channel. It will be a great help. Thank you.